Welcome back. In the previous lecture, we talked about Schrödinger's and Heisenberg's equations of motion in the general case, and more specifically about Schrödinger's equation for wave functions. In this lecture, we consider a 2-qubit example for illustration. So let us now look at an example that is a little bit more complicated than the single qubit example for the 2-level atom that we saw before. Let me think of a system that has 2 qubits. And so what are the dynamical variables? So we have the Pauli operators x, y, z for the first qubit. So let me call them x1 and y1 and z1. x1, y1 and z1. And then we have the Pauli operators for the second qubit. So let me call them x2, y2 and z2. And so let's take as the basic cats and bras that are labeled by 0 and 1, such that for a single qubit, such that z applied to 0 is to 0 itself, so this has eigenvalue +1, and z applied to 1 is -1, so it has eigenvalue -1. And then, of course, we know what x and y do on those states. So for the 2-qubit system, then a basis would consist of a state where we have 0 for the first qubit and 0 for the second qubit. And I now want to be particular about this and emphasize that this basis can depend on time. And then we have the cat which has 1s for both. And then we have the cats which have 0, 1 or 1, 0. And those would be our basis of 2-qubit cats. Now what kind of Hamilton operator could we consider? Well, think of x1 and y1 and z1 as components of a Pauli vector operator for the first qubit. So this would be a sigma, but for the first qubit, sigma vector operator. And then for the second qubit, you compose these three into a vector operator for the second qubit. So here we have a vector, there we have a vector. Hamilton operator is not a vector, but it's a scalar. So we should think of Hamilton operator. A simple example would be sigma 1 dot sigma 2. But those are quantities that don't have magical dimensions. Hamilton operator is an energy. So let's multiply this by a reference energy E. So we will consider a Hamilton operator, which is essentially the dot product of the two sigma vectors multiplied by an energy unit. Right, so let me write this out. So this is this energy unit, and then it is x1, x2 plus y1, y2 plus z1, z2. And if I want to be even more explicit, then it's the energy constant sigma 1 at time t dot sigma 2 at time t equal to this energy, which we take to be time independent, and then it is x1 at time t, x2 at time t, plus y1 at time t, y2 at time t, plus z1 at time t, z2 at time t. So this Hamilton operator has now this has now been written explicitly as a function of these dynamical variables, all referring to time t, and we have no parametric time dependence. So this Hamilton operator has no parametric time dependence, and then we know from the previous lecture that therefore it is a conserved quantity. It does not depend in time as a whole. So although the ingredients depend on time, this particular sum of x1, x2 plus y1, y2 plus z1, z2 will not depend on time. The individual ingredients very well may depend on time, and they will, but the sum is time independent. So now let's see what happens when we apply this Hamilton operator to one of those states that we have chosen to be in the basis. So what happens when I apply it to the 0, 0 state? Okay, so the x1 converts the 0 state into the 1 state. The x2 converts the second 0 into the 1. Okay? The y1 and the y2 also convert 0 to 1, but multiplied with I. And so we get an I times an I squared, which is a negative one. So let me just write this out. So we have the energy factor, and then from the x1, x2, we get 1, 1 at time t, and then from the y1, y2 applied to the 0, 0, that will give us negative 1, 1 at time t. And the z1, z2, well, both of them give a factor of 1 and do not change the 0, 0, so we have the 0, 0 at time t from applying the product of the two z operators. And we see that these two contributions take care of themselves. This difference is 0, and what is left is just the 0, 0 t multiplied by e. So the 0, 0 t ket is actually an eigenstate of the Hamilton operator. Now let's look at the 1, 1 ket. So here similarly, you apply x1 and x2, it turns the 1 state into the 0 state, and the x1 turns the first one into the 0, and the x2 turns the second one into 0, so we get 0, 0 at time t. The y1 and y2 also turn 1 into 0 with a factor of negative I, but two factors of negative I is just another minus sign. So we get 0, 0 t from the YY application. Now, the ZZ gives a minus sign on 1, but there are two minus signs, so together it gives plus 1, 1t. So here too, the contributions that we get from x1, x2 and y1, y2 compensate for each other. This sum is 0. And what is left is the state that we begin with multiplied by e. So also the 1, 1 state is an eigenstate of the Hamilton operator with the eigenvalue e. Next, we look at Hamilton operator applied to the 0, 1 ket at time t. So that's the energy. So now the x1 converts the 0 into 1. The x2 converts the 1 into 0. So we get 1, 0 at time t. The y1 converts the 0 into 1. The y2 converts the 1 into 0. One of those comes with a factor I. The other one comes with a factor of negative I. So, but I times negative I is plus 1. So we get plus the 1, 0 t. And then we finally apply the z1 and the z2 to the 0 and 1. One of them has eigenvalue 0. The other one has eigenvalue 1. The other one has eigenvalue minus 1. So together it's minus 1, and we have the 0, 1 t returned to us. And likewise, if we begin with the 1, 0 state and apply the Hamilton operator to this ket, we have the energy times, and now x and y convert 1, 0 to 0, 1, 0, 1 t and 0, 1 t. Again, there is a plus I and a minus I combining into plus 1. And the 1, 0, one eigenvalue negative 1, one eigenvalue positive 1, minus 1, 0 t. So of course, here we just get a sum of 2, so this is the 0, 1 t times 2, and likewise this is the 1, 0 state times t. So now let's combine all of this into a matrix representation for H. So here I'm summarizing what we have found so far. This is our Hamilton operator, x1, x2 plus y1, y2 plus z1, z2. We apply the Hamilton operator to the 4 kets in our basis, now written as usual as a row. And so the first one is just reproduced multiplied by e. Second one is reproduced multiplied by e. The third one turns into twice the fourth one, minus itself, and all of this multiplied by e. And the fourth one turns into twice the third one, minus the fourth one multiplied by e. So now we want to write this as a matrix acting on the original column. And of course, since it's a matrix acting, want to write this as a matrix acting on the original row of kets. And since it's a matrix that is acting on this row of kets, it will be a matrix that is acting on the right. Row times matrix is another row. And so the matrix that we have here is the matrix that represents the action of the Hamilton operator. And that matrix has an overall factor of E. And then for the first two entries, it's just giving us these entries back. And for the last one, we have minus 1 for themselves and a factor of 2 for the other one. So if this is our Hamilton operator, this is our row of basis kets, then the matrix representing the Hamilton operator is this matrix. And as we can see, the matrix itself does not depend on time. This relation with these coefficients that appear here is the same for all times. The coefficients 1, 1, 2, negative 1, 2, negative 1, they do not depend on time. So the matrix is time independent, which is just illustrating the case that we discussed, namely if there is no parametric time dependence in the Hamilton operator, then the matrix that we use to represent the Hamilton operator will not depend on time. So now we have a wave function, and for the wave function psi of t, we have the Schrödinger equation, which is this matrix multiplying psi of t. Since the matrix does not depend on time, this should be easy to solve. So if we look at the first component in psi, so that's the psi 1 of t, psi 2 of t, psi 3 of t, psi 4 of t, referring to the first, second, third, and fourth of the basis kets, we have equations for the time dependence of psi 1, psi 2, psi 3, and psi 4. What about psi 1? Okay, for psi 1, it's IH bar d by dt, psi 1 of t equals, and now applying this column to this kind of Hamilton operator, just looking at the first component, Well, that's just E times psi 1 of t itself. And also for psi 2, we have E times psi 2 of t. So if we begin with psi given to us at time 0, so we want to know the psi at time t as a solution of this equation, knowing what is the psi at time 0. Well, it's easy for the psi 1 and the psi 2 because we just find that the psi 1 of t is equal to e to the minus I divided by h bar, the energy times the time that has left, times the psi 1 at 0, because this is a very simple differential equation. And the same for psi 2. For psi 2 of t, we have e to the minus I divided by h bar e t psi 2 at time 0. Now, for psi 3 and psi 4, it's a little bit more complicated, and so we need a bit more space, which we will provide for ourselves. Alright, so now that we have empty space, we can continue. And we can now write down what's the time derivative of psi 3 of t. So now we have to take this matrix and multiply it with this column. And we look at what we get in the third row. So we have E and then minus psi 3 of t plus 2 times psi 4 of t. That's this minus 1 and this 2. And of course, that's not an equation that we can just solve all by itself, because the time derivative of psi 3 involves psi 4. IH bar by dt psi 4 of t is E, and now there is the minus sign for the psi 4 and the 2 for the psi 3. So it's 2 psi 3 of t minus psi 4 of t. Okay, so we have a coupled set of differential equations for psi 3 and psi 4. And so, of course, we could now apply any one of the general methods to go about this. But it's actually not so difficult to see that there is a simplification when we look at the sum of psi t of 3 and psi 4 of t. So what's the time derivative of this sum? Well, that's just the sum of everything that we have on the right. Now, if we add this up, then there is a 2 psi 3 of t minus psi 3 here, so it's a psi 3. So it's a psi 3 of t. And likewise for the psi 4, 2 minus 1 is 1 psi 4 of t. Aha! So the sum of psi 3 and psi 4, that's exactly the kind of differential equation that we had for psi 1 and psi 2 before. So we find that psi 3 of t plus psi 4 at time t, that's equal to exponential of minus 1 over h bar e times t, and now it's psi 3 at 0 plus psi 4 at 0. Okay. So next, we look at the difference of psi 3 of t and psi 4 of t. So here we have energy, and now we take the difference. So it's negative psi 3 of t, and we subtract 2 psi 3 of t, so that gives us negative 3 psi 3 of t. And here we have 2 psi 4 of t, we subtract negative psi 4 of t, that gives us plus 3 psi 4 of t. Okay, so psi 3 of t minus psi 4 of t, psi 3 of t, psi 4 of t with an opposite sign, a factor of minus 3, so it's minus 3 times the energy, and then it's psi 3 of t minus psi 4 of t. Okay, so this is again a differential equation of the same structure, except that we are now talking about the difference of psi 3 and psi 4. And where we had e before in all the other cases, we now have negative 3e. Well, so that means that psi 3 of t minus psi 4 of t is equal to e to the, and now where we had e before, we now have negative 3e. So it is plus 3i divided by h bar et psi 3 of 0 minus psi 4 of 0. And then, of course, we can take half the sum of these expressions on the left and get psi 3 of t. We can take half the difference of these expressions on the left and we get psi 4 of t. And so that's what we will do next. So let me just do what I just said I will do. What is the psi 3 of t? The psi 3 of t is the sum of these two left-hand sides divided by 2. So it must be equal to the sum of the two right-hand sides divided by 2. That means that there is the psi 3 of 0 multiplied by e to the minus I h bar et plus e to the 3i h bar et divided by 2. So we have half of e to the minus I divided by h bar et plus e to the 3i divided by h bar et multiplying psi 3 of 0. And for the psi 4 of 0, well, there is this minus sign, which means that we have a minus sign here. And if we want to know what is the psi 4 of t, well, here we have to take the difference of the two left-hand sides and divide by 2. So it will be the difference of the two right-hand sides divided by 2. But now look at this. Psi 4 at 0 comes with a plus sign here, comes with a minus sign here. If we take the difference, we have two plus signs. So we get this kind of term going with the psi 4 of 0. So we have e to the minus I divided by h bar et plus e to the 3i divided by h bar et psi 4 at 0. And concerning the psi 3 of 0, since we now subtract, this comes with a plus sign, this comes with a minus sign, so we have this combination for the psi 0 of t. So it's plus half of e to the minus I divided by h bar et minus e to the 3i divided by h bar et of psi 3 of 0. And now let's just take these four statements about four components of psi at times t in terms of these components at time 0 and combine them into one statement. So those are the equations that we found as the solutions of the Schrödinger equation for the list of probability amplitudes, psi 1, psi 2, psi 3, psi 4. So they are now all expressed in terms of their values at the initial time 0. And so if I now combine them again as a column, so we have the wave function psi of t. And then there are two contributions. One that goes with exponential factors e to the minus I h bar et, e to the minus I h bar et. We have that also here and here and here and here. And I collect all of them with this prefactor, and then there is a matrix that has just this 1 entries for 1 and 2. And for 3 and 4, we have these factors of half, 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 half that make up this part of the matrix. And then we also have this other exponential factor that goes with exponential of 3i divided by h bar et here and here and here and here. So there's nothing that goes with psi 1 and psi 2, so there are zeros only here. And where we have the psi 3 and psi 4, well, we have a plus half and a minus half, and another plus half and a minus half, and they make up this part of the matrix. So these columns that appear here, well, that's just the psi at 0, the psi of 0, as multiplied by the sum of the two matrices that make up these pieces here. So together that's a unitary matrix that takes us from psi 0, the wave function at 0, to the wave function at t. Now, on the way from the Schrödinger equation to this solution, we notice that there are two different time dependencies that appear here. One that goes with exponential of negative I h bar et, and the other one has exponential of negative I h bar, and then it's minus 3 et. So what's the significance of this plus e and the minus 3e? Well, those are the eigenvalues of the Hamilton operator, or the matrix that represents the Hamilton operator. So this matrix, I remind you, had this form 1, 0, 0, 0, 0, 1, 0, 0, and then 0, 0, minus 1, 2, 0, 0, 2, minus 1. And of course, we can immediately read off that there are two eigenvalues E that goes with those ones. But what about the eigenvalues of this 2 by 2 sector here? So if I just look at this 2 by 2 matrix that we have here, then this 2 by 2 matrix has a trace which is negative 2 and has a determinant that is equal to negative 3. And so the eigenvalues of this sector must be such that they add up to minus 2 and the product is minus 3. So the eigenvalues are plus 1 and negative 3. So the eigenvalues of Hamilton operator, or the eigenvalues of the matrix representing the Hamilton operator, those are E, and that appears 3 times, 1, 2, 3, and negative 3e, and that appears once. So the sum of all the eigenvalues for the Hamilton operator is 0. The trace of the Hamilton operator is 0. The trace of this matrix has to be 0, and indeed it is. The trace is the sum of the diagonal matrix elements, 1 plus 1 minus 1 minus 1. Together, the sum is 0. So that's fine. We have 3 eigenvalues e, and 1 eigenvalue is negative 3e, and those are the values that we see appear in the exponent here. Okay? So these exponents are of the form e to the minus I divided by h bar, and then there is an eigenvalue of the Hamilton operator times t. But why is that the structure? Well, let's just go back and remember where all of this comes from. All of this comes from psi of t, time derivative, IH bar, is equal the matrix for the Hamilton operator, psi of t, but this matrix does not depend on time. So this equation has an immediate solution of the form psi of t is equal to exponential minus I divided by h bar, the matrix h times t, and then applied to the psi of 0. So it may be a bit unusual to have an exponential factor of a matrix, but it's actually not so particular, because the exponential function, we can always think of it as a Taylor series, and then you just get the identity minus IH bar HT, and then half the square of the exponent, and 1/6 the cube of the exponent, and so forth. You add that all up. But of course, if we think of H to be a matrix with eigenvalues, and we use a basis in which it would be diagonal, which just requires diagonalization of this part, and we know how that is done, namely by taking sums and differences of psi 3 and psi 4, because that's what we saw has the simple time dependence. The sum has the eigenvalue e, and the difference has the eigenvalue negative 3e. So we could, from the beginning, use a basis in which the Hamilton matrix is diagonal, and then the exponentiation is just an exponentiation for every single diagonal matrix element. But one way or another, we end up with this unitary matrix appearing here equal to this exponential factor of the matrix for the Hamilton operator. In summary, we solved the Schrödinger equation for the 4-component wave function of a qubit pair. In the next lecture, we establish many properties of the qubit pair observables in preparation for studying their evolution in accordance with Heisenberg's equation.